At the height of New York's skyscraper race, no one had ever seen a tower crane. Yet 700-foot giants rose above the streets. The secret was steel beams hauled by steam-powered derricks, swung over city traffic, and fixed in place by iron workers balancing on skeleton frames. Why did crews risk their lives, working without harnesses, on beams hoisted directly from the curb? The answer reveals not just how these engineering marvels stood without cranes, but why every beam and rivet demanded nerve, timing, and deadly precision. What really forced builders to invent new methods, and how did it change our cities forever? Steel changed the very idea of what a building could be. Before the 1880s, city skylines were shaped by stone, brick, and iron, each one heavy, each one limiting how high walls could safely rise. The Bessemer process, developed in the 1850s, brought steel production out of the laboratory and into the heart of American industry. Suddenly, steel beams could be rolled by the thousands, each one strong enough to carry far more weight than stone at a fraction of the mass. By the early 20th century, this new material set off a race to the sky. Instead of relying on thick, load-bearing walls, builders began to assemble steel skeletons, networks of columns and beams that carried the entire weight of a building down through a series of precise connections. This skeletal structure allowed architects to reach heights that would have been impossible with masonry alone. The load path in these frames ran straight down through the steel, bypassing the need for massive walls and freeing up floor space for offices, shops, and apartments. By the 1910s, New York and Chicago were locked in a contest to see how high steel could go. The Woolworth Building, completed in 1913, soared to 792 feet, while the Metropolitan Life Tower and the Singer Building each climbed past 600 feet. All of these towers relied on steel frames assembled one beam at a time, each piece hoisted into place by derricks rather than cranes. The sheer volume of steel required for these projects was staggering. Mills in Pittsburgh and Gary, Indiana, rolled out custom beams on a schedule that stretched for months. Every shipment had to arrive in the right order, ready to be lifted from the street straight onto the rising frame. Steel's strength and flexibility made these towers possible, but it also demanded a new way of building. Every connection, every joint had to be engineered to carry the shifting loads of wind and gravity across dozens of stories. The result was a construction process defined by coordination, timing, and relentless supply. Without steel, the modern skyscraper would have remained a dream. With it, the skyline became a place where height was limited only by human ambition. And the next challenge was how to get all that material to the job site, ready for the iron workers waiting high above the street. Steel beams bound for New York skyscrapers began their journey in the mills of Pittsburgh and Gary, Indiana. Each piece was rolled to order, then loaded onto freight cars for a trip that could take several days to reach the city. Once the steel arrived at rail yards along the Hudson or East River, the challenge was only beginning. Manhattan's crowded streets left no room for stockpiles. Horse-drawn wagons, sometimes 6 abreast, threaded their way through traffic, delivering beams straight to the curb outside construction sites. In the heart of the city, space was measured in inches, not yards. There was rarely a vacant lot or open yard to store materials. Instead, beams were hoisted directly from the street to the rising frame above. This practice forced a kind of just-in-time delivery long before the term entered business textbooks. Every shipment had to arrive in the exact sequence needed for assembly. If a beam showed up out of order, it could not simply be set aside. There was nowhere for it to go. Work crews on the ground coordinated closely with foremen and ironworkers high above. A beam might be unloaded from a wagon in the morning and hanging from a derrick's hook minutes later. The derrick operators, using steam-powered hoists, swung the steel up and over the city's constant bustle, threading it between trolley wires and lamp posts. The entire process demanded precision, not just in engineering, but in timing and teamwork. Even a small delay could ripple through the schedule. If a shipment was late or a wagon stuck in traffic, Ironworkers might find themselves waiting on the beams needed for the next level. On the busiest sites, like the Woolworth building, dozens of deliveries might arrive in a single day. Each one was matched to a specific spot in the frame, and each was lifted straight from the street, bypassing the need for ground storage entirely. This relentless rhythm kept the city's skyline rising, one beam at a time. At the heart of every skyscraper job in the 1910s stood the derrick, a machine as vital as the steel itself. Unlike today's tower cranes, these derricks were simple in shape but powerful in action. Each one featured a tall mast, often 50 to 75 feet high, anchored directly to the steel frame below. 4 or more wire rope guy lines stretched out from the mast's top, tied off to the building's columns or heavy timber blocks on lower floors and even the street. These lines held the mast steady, fighting the constant push of wind and the shifting weight of every lift. The real muscle came from steam. Boilers fired up hours before dawn, feeding pressure to hoisting engines tucked onto the building's skeleton, or sometimes at street level. These engines turned drums that wound up thick wire rope, often supplied by Roebling, the same company behind the Brooklyn Bridge. A single derrick, working with a steam hoist rated at 50 to 100 horsepower, could lift 10 tons straight into the sky, swinging a beam from the curb up to the 30th floor in minutes. The rope, sometimes more than 1 inch thick, ran through a maze of pulleys at the masthead, multiplying the force and allowing precise control over each load. The layout was a study in balance. Every guy line had to be tensioned just right, using turnbuckles and shackles anchored to the steel. Too much slack and the mast would sway dangerously. Too tight, and the mast could bend under its own stress. Ironworkers checked the plumb with a simple bob and string, making fine adjustments before a single beam ever left the ground. Each anchorage, whether a bracket riveted to a column or a timber block set in concrete, had to withstand forces of 20 or 30 tons, a test of both engineering and nerve. What set the guy derrick apart was its ability to climb. As the building grew, the derrick could not simply stay put. Crews would unbolt its base, slacken and shift each guy line, and then, using an auxiliary hoist, lift the entire mast and stool up to the next floor. This process, known as jumping, could take a few hours. The mast would hang briefly in mid-air, steadied by its guy lines, before settling onto a new set of beams, ready to lift again. On the Woolworth building, derricks jumped every few floors, keeping pace with the rising steel. Each move required careful choreography, never fewer than 3 guys held under tension with men stationed at every anchor and a signalman relaying commands to the hoist engineer below. The derrick's reach was its secret weapon. From a corner of the frame, the boom could swing in a full circle, picking up beams from the street and placing them deep inside the growing structure. On tight city lots, this flexibility was essential. With no room to store steel, every lift had to be timed to the minute. The derrick moving beams from wagon to frame in a single fluid motion. Through this blend of steam, wire, and human skill, the guy derrick made the impossible seem routine, lifting 10-ton beams hundreds of feet high, one after another, as the city's skyline took shape. A steel beam weighing close to 2 tons hangs from the derrick's hook, swung skyward by steam and wire rope. It rises above the street, guided by tag lines, gripped tight in calloused hands. On the skeleton frame, 2 ironworkers, known as connectors, wait, boots balanced on a flange 12 inches wide, eyes locked on the moving load. A signalman, perched just out of the swing, flashes a quick hand sign. Down below, the hoist engineer eases the drum, and the beam floats closer, pendulum steady. The connectors pull the tag lines, twisting the steel into position and easing it onto the waiting columns. A slip, a gust, or a missed signal could send the beam swinging, but the men move with practiced calm. Once the beam is lowered into place, the real choreography begins. Drift pins, tapered steel rods are hammered into bolt holes, forcing the heavy steel into perfect alignment. The clang of metal echoes across the frame. Temporary bolts slide through the holes, wrenched tight by hand to hold the joint steady. This step alone can take 20 minutes, sometimes more if the holes resist or the steel flexes in the wind. Every connection must be true. A crooked beam means delays for the entire floor above. Now comes the riveting gang, a four-man team moving with the rhythm of a practiced crew. The heater stands at a small coal forge, flames licking at a nest of rivets. With tongs, he pulls a cherry-red rivet from the fire and arcs it through the air, a glowing streak against the city haze. The catcher, crouched on the beam, snags it in a blackened tin bucket, bare seconds before it cools. He jams the hot rivet into the waiting hole. On the far side, the bucker up braces a heavy steel bar against the factory head, steadying the rivet with his full weight. The riveter, wielding a pneumatic gun fed by hoses that snake up from compressors on the street, drives the tool against the glowing shank. The gun roars, flattening the end in a matter of seconds, mushrooming the metal into a perfect dome. Each rivet must be driven before it loses its heat. 10, maybe 15 seconds from forge to final head. If a rivet cools too soon, it is knocked out, and the process starts again. This sequence repeats rivet after rivet, connection after connection. A single beam might require a dozen or more rivets, each one installed in this rapid-fire ballet. On a good day, a single gang can drive more than 500 rivets, the sound of their work ringing out over the city. The pace is relentless. As soon as one beam is finished, the gang moves to the next connection, following the rising skeleton higher into the sky. It takes nearly an hour from the moment a beam leaves the street to its final, permanent lock in the frame. Every step, hoisting, aligning, bolting, riveting, depends on the crew's coordination and nerve. The building grows, joint by joint, held together by the unbroken rhythm of men and machines. The beat of steel against steel. 100 feet above the city, iron workers moved with practiced confidence along beams just 12 inches wide. There were no safety lines, no harnesses, only leather-soled boots, and the balance that came from years on the steel. Every step was a test of nerve and muscle. Lunch breaks happened right there on the frame, a sandwich in one hand and the city sprawling far below. The only thing between a worker and empty air was experience. Precision mattered at every moment. A 2-ton beam hoisted by the derrick could swing like a pendulum with the smallest gust or a misread signal. Communication was its own kind of lifeline. Voices vanished in the roar of steam engines and city traffic, so crews relied on hand signals, whistles, and the sharp eyes of the signalman. One hand raised meant hoist. A quick wave to the left or right told the hoist engineer which way to swing the load. Flags and megaphones helped foremen on the ground direct the flow, but at height, gestures and instinct carried the day. The signalman was the silent conductor of this operation. He stood where he could see both the beam and the hoist operator, relaying each instruction with crisp movements. Only the signalman spoke to the engineer, no one else interrupted. On a busy site, dozens of lifts could be happening at once, each one demanding absolute clarity. If a signal was missed or delayed, a swinging beam could threaten anyone in its path. Even a small error could turn a routine hoist into a life-threatening crisis. Iron workers guided beams with taglines, ropes tied to the load for control. They used their bodies to steady the steel, muscles straining against the weight and momentum. Every placement required teamwork, one man watching the swing, another calling out, a third bracing for the next move. Apprentices learned to read not just signals, but the subtle cues of the crew, the set of a jaw, the tension in a rope, the rhythm of boots on steel. Falls were common, the job was dangerous, but the pace never slowed. The culture on these sites demanded toughness and trust. Each worker counted on his partners to do their part, to catch a signal, to hold a line, to keep the steel moving and the building rising. In this world, precision and coordination were not just skills, They were the only protection a man had. At 792 feet, the Woolworth Building did not just stretch the limits of engineering. It tested the boundaries of what was physically possible with the methods available in the 1910s. Wind was a constant adversary. When gusts climbed above 40 miles per hour, every hoist was halted. A 2-ton beam suspended from a derrick could swing 15 feet or more in a gale, putting workers and the building itself at risk. During one storm in 1911, a sudden blast at the 25th floor forced crews to lash taglines to the columns and stand down for 2 days. No amount of money or management pressure could change the weather or speed up the careful process of jumping derricks and securing each piece of steel. Material supply brought its own set of limits. Steel orders for a skyscraper could take 3 to 6 months for mills in Pittsburgh or Gary to fill, with every beam rolled to precise specifications. Delays at the mill or on the rails rippled through the entire job. If a shipment arrived out of order, there was nowhere in Manhattan to store the extra steel. Each piece had to be hoisted almost immediately. The rhythm of construction was set by these constraints, not by the ambitions of architects or the size of a developer's budget. The scale of these projects was staggering. The Woolworth Building's frame alone required over 1,000 tons of steel in less than a week at peak pace. The Singer Building and Metropolitan Life Tower, both topping 600 feet, rose on city blocks barely wider than the towers themselves. Every lift, every connection, was a product of relentless coordination between mills, railroads, wagon teams, and the iron workers perched on the frame. The city's skyline became a kind of living schedule, each new floor a testament to the discipline and timing of hundreds of men and machines. But the cost was measured not just in steel and time, but in lives. Casualty records from the 1910s are incomplete, but the dangers were impossible to ignore. Falls, crushing injuries, and hoisting accidents were part of the daily routine. When the Empire State Building went up 2 decades later, 5 worker deaths were officially recorded, likely an undercount, but still a benchmark for progress. In the 1910s, most deaths went untracked, except in the ledgers of the Iron Workers Union. Widows' funds, first established in 1906, offered families a few $100s, often $500 or less, raised directly from the pockets of fellow workers. Union pressure slowly pushed for better safety, but change came in increments, not leaps. The buildings that still stand today are monuments to that risk as much as to engineering. Every beam, every rivet is a record of skill, sacrifice, and a system that worked because it had to, within the hard limits of wind, material, and human endurance. Today, nearly every skyline still rests on frames set by calloused hands and steam-powered derricks, built without modern cranes but engineered for endurance. As cities push ever higher with new technology, these century-old towers quietly prove that human ingenuity, not just machinery, shapes what lasts. The steel above us remains a daily reminder. Progress rises tallest when skill and courage do the heavy lifting. Thanks for watching. Share your thoughts below.